you'll see.
ได้ต้องเขียนอีเมลเลยครับ
There's a problem. I think partial t epsilon should be df, the Jacobi of f times the expansion of f prime x bar top t.
I'm sorry, say again. Did I do something backwards, perhaps? Say again.
I don't think the Jacobi should appear on the, on that part should be the Jacobi of f times, the right part of epsilon t. I think that's true.
I'm sorry, I mean, you may be right, but so far I don't see any error. It looks right to me, but maybe I'm wrong. Tell me.
I'm just a little confused. I think the partial derivative of epsilon should be.
But the partial, there's not an epsilon to be taken. Epsilon is a quantity. We're taking the partial derivative of f, this function f, and we're taking it now in an n-dimensional setting. So epsilon is a vector.
Yeah, because I think that the Jacobi should appear on the, on the times f. Yeah, I don't know.
I'm sorry, I really, I don't understand what you're saying. Why don't you get up and show what you're trying to say?
I'm not sure, but
No, I know you're not sure, that's okay, but you're welcome to ask. You don't have to be right to ask, but show me what it is you mean. I don't understand what you mean.
I don't think it should be here. It should be this times f prime.
Ah, yes. No, you're absolutely right. Yeah. No. Absolutely. Excuse me. Sorry. Thank you. No. So there's nothing wrong with that. This one's right. This is what I should have written. Not the time derivative. Yes? Now you're happy?
No. You mean?
This is the formula for epsilon of t. I had written dt epsilon.
Yeah. Okay.
Yes, that's what you were saying.
Yeah.
Yes.
Yeah. I'm just from the calculus. I think is there something?
No, but hold on. You're happy now? No, but really, no, tell me, because before I was wrong.
No. I just try to correct, make something.
No, but you're not answering my question. Do you think it's right now?
Yeah.
Yes, okay. You're sure? Don't hesitate. Look, you corrected a mistake of mine. You have a right. If I'm not right, I was wrong once. So this is okay?
Okay. Yeah.
This is okay.
Okay.
Yes, okay. You see, I had written dt here instead of epsilon. Yes.
If it's dt on the left side, then it will be df.
That's right. That's right, exactly.
It will be df with the epsilon.
Right, that's right. Here we would have written dt epsilon is equal to df bar epsilon.
Yeah.
Right. This and these two things are basically equivalent.
Yeah.
Right? Yeah, okay. Right. So I think you see from my reception of his question that you should all not hesitate to ask questions. They can be very useful. Right? Okay? Yeah, okay. So, yes, right, this is the, okay, so getting back then to what we're doing here, the point is that we're doing this in a concrete case. The x bar, as we said, was this basic solution, the motionless solution that we called stars before. The epsilon is now what we're calling psi and t, and these equations here are like this equation here. Okay? They're saying the time derivative of the perturbation, and here psi and t are perturbations, meaning that they're small deviations from the basic state. And this is this matrix notation is just a general notation for any kind of linear operations on the right, which these are, even though they contain spatial derivatives and all, but that's also linear operations. And the solution to that is going to be of the form exponential of that matrix, which, and we haven't written it as a matrix, but that equivalently, but it's going to be equivalent to that, times the initial condition, and there will be growth if any of the eigenvalues are positive. Okay, so we, because of the boundary condition, Okay. In all this that we did before, there was no spatial aspect. We treated these epsilons and these x bars as just a column of vectors. Now, psi and t, they're a bunch of numbers, but they're organized as having values on an x and z grid. But they're still a bunch of numbers. Psi and t are a bunch of numbers that occur on the x and z grid. Oh, but so it doesn't seem.
Have you got the power onto your laptop?
I'm sorry, say again?
Is your laptop charging? Yeah.
It seems if I don't change it often enough, somehow it loses its thing, and then I have to push in
Yeah.
the HDMI.
Come back.
No? Okay. All right. So the boundary conditions on psi and t that we've spent so much time discussing then lead to the spatial form for these solutions. We already said that the things that that sine k pi z satisfy these boundary conditions of being 0 here, and the second derivative in z being 0. And what we didn't say, but which is the case, is that it's a complete set, that anything that satisfies those can be expanded in that form. So that's this dependence. We talked about being periodic in the x direction with wave number q. But the fact that, so we could have written a general periodic function, sine q x minus x naught. But here we have written a particular one just because we are allowed to fix the phase. And the t has the opposite phase. Why is that? Well, you see that the x derivative of t occurs in the psi equation, and the x derivative of psi occurs in the t equation. So they are out of phase in x. So these are the general solutions to that once you've fixed a phase. And the fact that I've just come out with these, this is as general and as true as the fact that when you have a constant coefficient differential equation, you know that the solutions are exponentials, right? Exponentials in a generalized sense. If that lambda of the exponential turns out to be imaginary, then they're trigonometric. And these equations are constant coefficient equations. They would not be if, they're constant coefficient equations for t and psi, and hence their solutions are trigonometric they could be exponential, but then they wouldn't satisfy the boundary conditions. The kind of exponential that they are trigonometric. Okay. And okay, this part probably doesn't shock you at all, and I should have started with that. The fact that we have a first derivative here, a constant coefficient, first derivative in t, and hence the solution, and no other derivatives in t, hence the solution is an exponential, for the same reason that we knew that this was an exponential. This is what solutions of first order constant coefficient equations look like. So this part doesn't come as a surprise, and this part should also not come as a surprise because it's also constant coefficient it's not quite as obvious, but it's still constant coefficient as concerns x and z because you only have the derivatives. We can talk about that further if you have any questions. Now, we have new quantities, again, overlaying notation. I put hats here, which are merely amplitudes. The psi hat and t hat are constants in front of these functional forms. These are not the same hats as were used in for the deviations before. Okay, these are scalars, and these are functions of x, z, and t. When you substitute these expressions into these equations, you're going to get a lambda from here. The Laplacian is going to be minus q squared minus k pi squared, and hence minus gamma squared here. You're going to get a q here and a minus, in fact it's a minus q because derivative of cosine is minus sine, so minus q. And here you have Laplacian squared, so you have gamma squared and gamma to the fourth. The time derivative brings down a lambda, and here you have a q that comes from the fact that sine qx is q cosine qx, so you have a q, and here you have your minus gamma squared. So having taken, you have these equations that were, I would say, infinite dimensional, meaning that they, even though it's, I mentioned this yesterday, there's two spatial dimensions, x and z, but in the framework of dynamical systems, dimensionality means how many unknowns do you have, and here you had psi and t on a whole grid of x and z values, hence this was an infinite dimensional, or if you were doing numerical, a simulation of it, it would 1,000 dimensional, say, dynamical system with 1,000 values to be determined of psi and t. But because we know, we've chosen the simplest possible boundary conditions because we know something about x and z derivatives, the Laplacians and all those things, we have reduced it now to a two-dimensional system here. And now we see that this really is, it wasn't so obvious how this was a matrix, an infinite dimension, well, I shouldn't say matrix, not for mathematicians, I'm here in a math building. If you have an infinite dimensional system, then you don't call it a matrix, you call it a, what do you call it? There's a word for it.
Operator or?
Another word, what's the word I'm looking for? I'll think of it.
Some kind of operator, no.
It's, I'll think of it. Okay. But, you know, big matrix. Anyway, now it really is not just a matrix, but a small matrix. This is 2 by 2. You can see that this is a 2 by 2 system for the scalars t hat and psi hat. So this, it's going to drive me crazy. You know, it's that thing, right? You know how you write these things? Like that?
Yeah.
What's that word?
Oh,
Variation.
none.
That's variation.
Right now it's going to drive you nuts too. The one that you write like that. When you see, he's being driven crazy. I shouldn't have done
I've got a
that.
laptop, I can look it up.
Okay, yes, you can look it up. This thing you know. Okay, anyway. So now we really have a 2 by 2 system, which has been written here as a matrix system right there. Yes?
I just have a very short question. Why you introduced the gamma in the previous slide? Is that just simplify the equation?
Just to
or-
simplify the equation.
Okay,
That's
so
all.
it might have some
Yeah.
physical meaning.
No,
in the
no,
future.
no, no. It's just simplify the equation. And here we've divided through, I'm glad you mentioned that, because you see here that we've divided through by gamma squared so that we don't have a gamma squared into the top equation there. Okay? So this is what we really have. We recall that this lambda is the temporal growth rate, is a 2 by 2 matrix. And you recall that we said, again, back yesterday with the, when we were doing basic dynamical systems, we said the system is stable when f prime of x bar is negative, so that perturbations decrease. It's unstable when f prime of x bar is positive, so that perturbations increase. And at the point where f prime of x bar is 0, the boundary between stability and instability, that's when you have a bifurcation. We define bifurcation to be the change in number or stability of equations. So we're looking for where f prime, in the scalar case, where f prime of x bar is 0, or we are looking in the case of a multidimensional system for when one of the eigenvalues of the Jacobian matrix is 0. Okay. So let's do that. Let's set lambda equal to 0 over here. And so what that gives us is just, okay, if lambda is equal to 0, that's, you don't even have to, you might think, oh, I'm going to find the eigenvalues of that system, and you can do that. You can find the eigenvalues of that system, but you can very easily find the 0 eigenvalue because that requires the determinant of this matrix to be 0. So here's the determinant being 0, and you learn, and if you, you can rearrange it such as to get Rayleigh number equals gamma to the 6th over q squared, and you have this physical result that the instability does not depend on the Prandtl number because the Prandtl number just multiplies the whole thing. And this is well known that the threshold for convection does not depend on the Prandtl number. And so you learn that this is the critical Rayleigh number, gamma to the 6th over q squared. And we call that Rayleigh critical of q and k. So what does that mean? What does that mean? Over, again, back here, we discussed an infinite dimensional system with lots and lots of different eigenvalues.
What is it the name for it?
variational something.
differential.
No, but
a
the
functional
Frechet derivative. That's it.
derivative.
Frechet. That's it. The Frechet derivative. Right. In the infinite. That's right. If it really were infinite, Frechet. But here it's just a Jacobi as a matrix of partial derivatives. Frechet. That was it. Okay. Anyway, what does this mean? Again, going back now to this infinite case, before we specified Q and K like this as numbers, this equation doesn't have Q and K specified as numbers. This equation encompasses this one for all Q's and all K's. This is one possible part. That is to say, you can if you wrote it right, you would write that matrix corresponding to the full one, you would write it in this way for a certain pair of QK values. You would have this system here. A different pair, you'd have this. You'd have and zeros every place else. You'd have a bunch of different decoupled matrices. And of course, this goes on to infinity for all Q's, all K's, doubly infinite. K takes on only integer values, but Q takes on any values. So this is really, really very infinite, this matrix. Okay, and that would be the matrix that corresponds to this full system. So it would have many, many eigenvalues, right? It would have, okay, we will call here some I'd like to interject lots of results about matrices here. Recall that, okay, this matrix is block diagonal. It's not diagonal, but block diagonal. There are little blocks along the diagonal, right? And the eigenvalues of a block diagonal matrix are the eigenvalues of each of the individual diagonal matrices. So having found, this that we wrote here about lambda for a specific Q and K, this has to do with eigenvalues of one specific block, the one corresponding to specific value of Q and K. And so what does this tell you here? This says this is the okay. Remember, we're looking for when the eigenvalue crosses between negative and positive, meaning when it's 0. And this happens for a particular block, say this one, labeled by some Q and K, when this Rayleigh number has this value. For a particular block here, let's say we're just going to investigate this one, for a particular one, when the Rayleigh number has that value, the one of those two eigenvalues becomes crosses through 0. Okay? Now, how do we put together, this is a question we had last time, we said, okay, we have all these eigenvalues, when do we have stability, when do we have instability? And we answered the question, it's when a single one of them becomes positive. So we do this for all the different blocks, and if any of them is positive, then we have instability. Meaning that the perturbation that looks like this, that has this particular K and this particular Q, is going to have go from having negative to positive growth rate, and you'll have instability to a transition to instability. That perturbation will grow. That particular Q and K will grow. And if you grow to any Q and K, then you're unstable because you assume that as the truck passes by your experiment, it's emanating perturbations of all Q's and K's. So any Q and K that grows, you're going to have instability. So that is the information that's here. How is that? Well, we can take this function, Ra of Q and K, and we have instability to a perturbation with geometric dependence Q and K will grow if Rayleigh number is bigger than this RAC here. And for different K values, because K has to be an integer, we have drawn that RAC as a function of Q. And so for Rayleigh number above this curve here, okay, let's say, if you're looking for growth of a K equal 2 perturbation at Q equal 3 pi square root of 2, you look to see if you are above or below this curve. Okay? And if you're looking for perturbation, for growth of a pi over square root of 2, q equals pi over square root of 2, k equal 3 perturbation, you look to see if you are above this curve. But if you are then interested to know if you are stable or unstable to all perturbations, what you need to do is to be above all the curves. And that is achieved if you are above, the lowest one is here, and if you are above this point, then you are above some curve. In particular, this k equal 1 curve, which turns out to be the lowest. You're above this, and so hence you are unstable. So Rayleigh number, any place above here is above some curve, and hence you're unstable. This is the critical Rayleigh number. Not the critical Rayleigh number for that q and k, but the critical one. It's the minima of all of these points. And it's here. And we can write it analytically because this is a simple expression here. What we need is to find the minimum of this curve, and that is easily done. First of all, the minimum is found for k equal 1, but then when we differentiate with respect to q, to find the minimum, we do all this. We have this expression, chunk, and we get this q. This is the minimum for each of those k's. That's to say, those dots on the previous plot, those dots plot those particular q values here, and the minimum is to be found for k equal 1. And hence, that value here, you can see from this it's between 100 and 10,000, but more specifically, it's equal to 657.5. Yes?
But we won't have anything below k is equal to 1, right? Because k is the mode numbers. It starts from 1, 2, 3.
Yes?
So it means that technically our Rayleigh number would be just limited by this line. We won't be in the stable regime.
I'm sorry, I don't understand.
So k's are basically the modes, right? 1, 2,
Wait,
3.
maybe let me draw what, just a little picture just for, okay, here. K equal 1 are things that look like this. K equal 2 are things that look like this. K equal 3 are things that look like this. Okay, k equal 3, k equal 2, k equal 1. Okay, this is here, this length is 2 pi over q. Okay, so what were you saying then?
Okay, I was trying to say that since k is equal to, these are distinct modes. K is equal to 1, k is equal to 2, k is equal to 3 are discrete modes.
Yes.
So we have some discrete values of Rayleigh number as well, right?
But not in q.
Oh, okay.
But not in q, because for q we are allowing to have any value. The k equal 1 has these are discretized values because you have made a distance between the plaques here, and you would have discretization also in this. Q is a wave number in the x direction. You would have discretization also if you had walls in the x direction, if you had imposed a length. But we haven't. Okay, we can impose a length, a periodicity length of q, in which case we would discretize these q values. Instead of allowing them to take on any value here, we could say, oh, my length is going to be, I don't know, L, and then we would have, these q's would have to have values 2 pi over L, and we would choose this, and this, and this, and this, some grid in the x wave number. That answers your question then? Yes. I think this was perturbing when I first learned it, this asymmetry between the treatment of x, of the vertical dependence as integers and the horizontal dependence. But that is just the construction of the problem. You decided to treat all the q's at once, have any periodicity length. If you had fixed this, then you would have this, you would have discreteness in the x direction just as you have in the z direction. Like you, I need to turn off the phone.
Sorry, doesn't that mean that we just sit on any given curve? So for k
I'm sorry,
equals
hold
1
on just a second. Let me not be disruptive. Let me turn off the sound. there. You were saying?
The critical Rayleigh number is dependent on Q and K. So if we fix K at 1, it doesn't matter what Q value we take. We're always going to be sitting on that K equals 1 curve, aren't we?
That's right, but you still would want to know when you are, okay, what should I say? Okay, let's perhaps talk about his point. Supposing we had fixed our Q, our X length, then we would not be allowed all these Q values. We would have only specific ones, only a specific grid of them, and we would have a set of points like that. But maybe that's not, perhaps, ask your question again.
That for any given K, it doesn't matter what our value Q is, we'll always sit on that curve. We won't be able to occupy any space below the curve because we fixed K equals 1. Is that?
Well, okay, we don't fix K equal 1. We are allowing, as far as geometry and boundary conditions go, we're allowing any of these. Say, we don't know for sure that the system doesn't want to do this. Maybe it doesn't want to do this. Maybe it does. Maybe this is what it wants to do. Maybe this has a lower threshold. Or maybe this has a lower threshold. Maybe this is what the system wants to do. It turns out, once you do the calculation and you draw these curves, that what the system wants to do, and what does it mean the system wants to do? The idea is you're increasing the Rayleigh number, and when does convection begin? It begins when you hit one of these curves. And the first one that you hit, it turns out, it's not by construction, it turns out that the first one that you hit is the K equal 1, meaning this is what the system wants to do. If you prevent it from doing this, well then it'll do this.
Okay.
So you're not stuck on a curve because they are contours of the
Of-
eigenvalue.
Yes, that's right. These are contours of, these are curves
Zero.
of lambda equals 0. And this is a result of the calculation. It's not something that you imposed. What you imposed is that is that K be an integer? No, well, no. I mean that's part of the construction of the problem is that you're between two plates, and this is your length of 1, and hence you okay. But it's the system that has chosen to do something K that prefers to do K equal 1. And you can prevent that, and people sometimes do in other, mostly in the horizontal directions. Suppose you, instead of having your plugins, somehow you had some very long thing that, so it was kind of like, kind of infinite, but you did something where you kind of put I don't know, some very subtle magnetic field or something or other that really favored, but barely, two rolls, one on top of the other. If you kind of prevented it from, you see that a single roll crosses the midplane. If you somehow prevented it from crossing the midplane by I don't know what means, then it's going to say, well, you know, I kind of like to do this, but I can't do this. I'm not allowed to cross the midplane, and it would do this. But you'd have to, I don't really know how you would prevent it from doing that, but if you somehow could design an experiment that would prevent it from crossing, I don't know, have some kind of mesh or something, but how's that different from having a different K? I don't know. If you somehow managed to put some mesh that would keep it from going across this, then it would do this.
I mean, correlating these things to the actual phenomena, suppose we have a hot end and a cold end, we keep the cold end fixed, and hot end we start increasing the temperature, that is we are changing boundary condition. So at a point when the convection starts, does that mean that at that boundary condition we have hit the K is equal to 1 curve or some other K is equal to 2 curve?
Okay. I've always noticed this. You go to a seminar, people are asking questions. The seminar speaker never understands the question. You in the audience, you may have not understood the seminar at all, but you understand that question that the person was asking, and you see that the seminar speaker is addressing some whole other thing. And so too, I must confess, I don't understand your question. Explain to me.